Thank you and good morning to everyone here. I'm really excited to be able to tell you about this renewed search for life outside the solar system in particular, and our goals for the very near future of one of these historic opportunities science has given us to search for life, alien life. And so it is an old question, what is the origin of life on Earth, although that's a historical question which may be difficult to pin down. But the more general question, how does life emerge and what is life as a phenomenon, part of that array of physical, chemical phenomena that science has been able to uncover in the observable universe? That's a big question, and it's finally open to the tools of science. And that happened relatively recently, as you will see in what I'm about to say. So let's pin down the two questions that should be in your mind while I'm talking. The first one is there life on other planets? That's an easy one. The second one, which is really the difficult one in this case, is how do we know when we see it? And so I'll try to cover both of these questions for you in kind of 4 parts. Let's start with the most difficult one, which is, do we have a definition of what life is? And the answer is no. However, I'm sure that each one of us has kind of in their mind a favorite way to describe this phenomenon. So think for a minute what your favorite definition is. When I said we don't have a definition, it's not for the lack of trying. It's just nobody in the science community, or elsewhere for that matter, agrees on a single one. So that's why we don't have one at this point. We just have too many, which are not always compatible with each other. So what is the issue here? Well, the issue is that we have to think both from the point of view of how do we describe something in the fossil geological record as life, versus how do we describe something we see remotely away from the Earth as life. The first part is relatively easy because we are talking about the same single one case of that unusual phenomenon here on Earth. So we are all interrelated very nicely through the tree of life. And people, paleobiologists, have actually managed to do a pretty good job in using morphology, crystallography of the different minerals that are left over in the rocks, molecular signatures and others to tell us what are the ancient forms and ancient evidence of life on this planet. But it's not very much different from evidence that we'll be collecting in the solar system from Mars and other places where we expect maybe life emerged. It is, however, different from what might have happened on other planets beyond the solar system. The chemistry intrinsically may be different, and then we may have very different situation when it comes to what builds the structures that then we see as a biosphere. And so, as I said, there is no agreed upon definition. So probably your guesses or thoughts as valuable as anybody else's. So what about your favorite definition? And how do you think about life from the cosmic perspective? How would you define it if you had to answer that question? Let's see if somebody has some thoughts. Remember, there are no wrong suggestions here. As I told you, nobody agrees on a definition, so you don't have to use Wikipedia because you won't find one. Yes?
Something that uses energy.
Something that uses energy?
Something that has a metabolism.
Something which has a metabolism. Catalysis, maybe, perhaps something of that sort. Thank you.
Something that reproduces.
Something that reproduces. That's a different one. You probably need energy to accomplish such a complex task. Yes?
Something that is susceptible to Darwinian evolution.
We are talking now about very particular type of development. You need replication, you probably need the energy, and you always need energy. Yeah, you see, it's difficult to come up with a single obvious thing, although there is life all around us. We know its history on this planet. Its diversity is large enough that we don't just have one data point. Historically, we can actually see how many of these features, the use of energy, the ability to reproduce, Darwinian evolution, actually have worked their way through. But it's very difficult to pin it down as a phenomenon, and probably for good reason. We really only know of one single example, whether it's out there in nature or in the lab. And so this is what a lot of this search is all about, to try to solve that problem. So it is still good to know what you're looking for and where you're heading. I myself have a favorite sort of definition, and that's sometimes called the NASA definition, and that is that life could be defined as a self-sustained chemical system capable of Darwinian evolution. The self-sustained comes to your point about energy, using energy and metabolism. The chemical system is particularly important to me because it describes it in a cosmic sense from the point of view of astronomy. Darwinian evolution combines what you suggested and what, of course, you said there particularly. And in the end, all of this comes together in a package which has very specific behavior, which you suggested as your favorite definition. So it is not necessarily the individual attributes you see. It's the system that ends up behaving that way. So how could a system like that emerge when we know systems which are well organized, like crystals and flame in a certain sense, but none of them gives us the full package? And what I want to do here, partly because this is my background, and partly because that's where a lot of the new motivation for this scientific exploration comes from, I'm going to give you the astronomical perspective. And the astronomical perspective focuses on that particular part of the definition here, which is the chemical system, that life is a chemical system and has a particular set of attributes, at least as we know it. This list of attributes lists essentially what we see in life on Earth today and in its history being essential. And it describes Darwinian evolution in kind of a more generic way, which is one of those very important breakthroughs in science of 150 years ago, which, as Einstein pointed out for his own general theory of relativity 100 years ago, it's too good and elegant of a theory not to be realized in nature. So Darwinian evolution is particularly interesting from that point of view, because it not only allows for the phenomenon to be adaptive and self-optimizing, which is what it actually accomplishes as a system, but actually does not require necessarily all the whole package to exist. In other words, we now know from experiments in the lab that you can reproduce all the aspects of Darwinian evolution at the molecular level, not at the level of a cell or a population, which would call living entities, but simply of molecules which, by any definition, are not living, strands of RNA in particular. So Darwinian evolution is really conceptual, if you want, mathematically backed paradigm in science, which is very important, but maybe not necessarily central by itself to the phenomenon. So that's why, while a lot of people would use as their favorite definition the emphasis on Darwinian evolution, there is still disagreement as how central it is. So one way, especially from the astronomical perspective, to reduce that to kind of evidence that we can count on, at least as a basis for this discussion, is to concentrate not on the complexity that leads to the tree of life or the donut of life, because we don't really have the root yet. And we may have difficulty finding the root, which is the empty hole in the middle. All life is, as we see today, is the surface of that. It's not that complexity, but the simplest part, which is that life on its basis has to be a chemical system. And it brings me to the cosmic limits for life, or the limits that are imposed by the observable universe, generally described by astrophysics. As you already know, the observable universe is really dominated by three basic entities. The ordinary matter, which we all know and love and part of, or baryonic matter, but that's the smallest in terms of total, just shy of 5% of total. And of course, dark matter and dark energy. As it turns out, we know enough about dark matter and dark energy to say that the complexity which is necessary for even part of the package that we call life on our planet is not there. So in the different scales of the observable universe, from the largest scale, which is the galaxy superclusters, where everything is dominated by the force of gravity and essentially by dark matter, not by the baryonic ordinary matter, which is on the top there. You go through a progression of then galaxy clusters, the galaxies themselves, our own galaxy, the Milky Way galaxy, which is still fully under the domination of the force of gravity, and to a great extent, down to the level of large galaxies by dark matter still, not ordinary matter, down to the level of one of the most important, but also significant components of the observable universe, which are the stars, where for the first time, you have a pretty good match between gravity and the next fundamental force in line, which is the electromagnetic forces. But what is important about this hierarchical structure is that when it comes to what determines its baryonic components, it's very simple. It essentially consists of hydrogen and helium. And that is true not only as a snapshot of the universe at large as we see it today, but also as a history, and particularly emphasized as a history of the universe. The universe is completely dominated by hydrogen and helium, while it's only recently in the history of the universe that we have enrichment in the rest of the chemical elements. And that are, of course, the important elements of oxygen, carbon, nitrogen, which come as the major next in line in these cosmic abundances, as we call them, as we see them today, and which are true for any census you may take of the galaxy or of the stars that are a major component of our galaxy, and of course the material around the stars. So the important point here is that we know enough chemistry to be certain that hydrogen and helium and another noble gas, which is very common, neon, are woefully inadequate in building any structures. Any structures which could do most of the things that you and I describe as essential to the phenomenon that we are trying to define here, life. There are many ways to put this, either mathematically or simply by looking at the possibilities that are given by these two elements, hydrogen and helium. It just doesn't work. In that sense, it's similar to dark matter. It's even worse. The fact that there is 5 times more dark matter in this universe doesn't do anything for life, except defining the big stage. But when it comes to the phenomenon and its emergence, what you need is the table of the elements. And this is a particular table of the elements which highlights which of the elements is essential to life, either structurally or in bulk. Like hydrogen is important to life, but so are oxygen, nitrogen, phosphorus, and of course carbon. And there are some elements which are essential. So you see, the point here is that the universe has to come to a point in its evolution, in its development, expansion, and chemical enrichment for the phenomenon to even have a fighting chance to get started, whether to emerge or sustain itself. And in that hierarchy of structures, both in scale as well as in time, the first time and the first place in that scale where the break from the dominance of hydrogen and helium occurs are the planets. So the next object of importance in this observable universe, a very numerous object, are the planets. The planets which have the concentrations of metals, as we astronomers call them. We call everything heavier than helium a metal. But it really works in this case because that's what I'm talking about. We have to go to the planets. And concentration, as you will see in a minute, is a really important, very important concept for the emergence and even the sustainability of the phenomenon, but particularly for the emergence. So you have here the chemical bond that allows the complexity that would lead to the self-adaptive, self-sustaining system capable of using energy from the environment, capable to create a software out of this hardware, the chemical bonds, which will write and create its own hardware, which will make sure that the software is still there, which will make more hardware based on this software. So that concentration is the planets, and I'm making a very trivial point to many of you because you'll say, but we knew this all along. For 50 years now, we've been saying we should be looking out for life on planets. But I think it is important to remind you that our most recent knowledge of the properties of dark energy and dark matter have only emphasized that good guess people had 50 years ago, that planets are the place where life happens and that life is a planetary phenomenon. That everything, all those revolutionary developments in astrophysics that have happened in the last 50 years have only very strongly emphasized the same point. In this universe, you should be looking for emergence of life on planetary surfaces as part of the planetary geochemistry. And that makes it easier then to go out and do the next step. Where are those planets? Where are the planets which really have the concentration of the elements we are looking for? Stars don't do it. And in fact, turns out very big planets like Jupiter and Saturn don't have enough of a concentration either. Whatever they've managed to concentrate in terms of metals, as we astronomers call it, generally ends up near the core of the planet, and they don't have surfaces to start with. There is too much dilution in hydrogen and helium in the majority of the volume of a planet like Jupiter. So what we are looking for is generically now called super-Earth planets, like Superman, but you know, in science, quite often those names come somewhat unplanned, and this one stuck. So we call them super-Earths because they're simply larger in size and mass than our own planet Earth, but otherwise have similar characteristics. They're generally rocky. They have some amount of water, sometimes more than what we used to. And they're roughly in that range between what we call a rocky Earth-like planet and the giants. The smallest giant planets in our solar system, Uranus and Neptune, and they're very different. They're also larger in size, 4 times than the Earth. So we're talking about a gap here in the solar system, in our own solar system, where the only representatives of this family of super-Earths are Earth and Venus. And actually, they're on the small scale compared to what we see around other stars. And what we see around other stars, we see a multitude of those planets. In fact, the super-Earths as a family are currently the most numerous type of planet we see out there around other stars. It's just a fluke that in our own solar system, the Earth is the largest one of those. Just happens so. These are initial conditions which lead to that. So here, one example of many that the NASA Kepler mission has produced, Kepler 62. It's a system of 5 currently known planets. All of them transit the central star. That's how Kepler detects those planets. And 2 of those, 62E and F, are slightly bigger than the Earth in size. You see the sizes of the 4 terrestrial planets in the solar system compared to the 5 planets in Kepler 62 in real comparison. You also see the orbits in scaled comparison here, where you see the inner planets, again, of the solar system. And Kepler 62 is to scale there. The reason we have the green zone, which, by the way, has a name. We call it the habitable zone, simply because the Earth happens to be in that particular zone in our own system. But more seriously, this is the distance from the star, the Goldilocks zone, as some refer to, where the planet is not too close to the star that the temperature is too high, so all water would evaporate into steam, and not too far away from the star where all water will freeze permanently above or below ground. So in our solar system, Venus is a little bit too close. Mars is right okay, normally, not too far, but because such small planet, it's not super-Earth, it lost its atmosphere. So it cannot really warm through greenhouse effect mostly the surface enough so that the water be in liquid state. As you know, there is a lot of discussion about was Mars wet and warm in the past. It seems the answer is yes. We see a lot of evidence for that, and certainly there is water. Why are we obsessed with water? Well, if you saw there in my list of attributes, life as we know it uses molecules that function in water. They emerge in water, it seems, and they certainly function in water as a solvent, in water as a source of protons, in water as a polar liquid. But, you know, why not some other liquid? How about liquid methane and liquid ethane? The lakes of Titan, the large moon of Saturn. There's such lakes out there in our own solar system. Why should we be so particular about water, which essentially defines this green zone, the habitable zone? There is another reason why, and it's astronomical. It comes from my field again. Water is the most common simple molecule out there because it consists of 2 of the most abundant elements in the universe as we know it today, hydrogen and oxygen. There's helium in between there, but can't make water out of helium or anything useful for that matter. So there is plenty of water everywhere. So first you will find water, and only then ammonia and methane and ethane. So water is very common, and from a practical point of view, makes sense to look for that. So the current sample of dense exoplanets, let's really go to the point where we actually look at the data about these concentrations of metals, the rocky planets. That's where we are as of this spring. That shows you a diagram of planet mass in units of Earth masses compared to planet radius in units of the size of the Earth radius. And you see those colorful dots there with error bars. It's very important here. It's very difficult to do those measurements. Sometimes you see that the error bars on the radius are very small, very good measurements of the radius. Guess what? This is what a $500 million NASA mission does for you. That's the Kepler mission success story, which gives you a lot of the sizes very precisely from the way in which it discovers and measures the planets. The mass is a little bit more difficult, especially for the planets that are closer to the Earth, the smaller ones. For that, we use big telescopes and precise measurements from the ground. And it helps if the planet is more massive. But let me tell you why I'm showing you this diagram. The reason I'm showing you this diagram is because those colorful lines, curved lines that go through the data there, are lines of equal composition. In other words, the bulk composition of the planet would scale with mass and radius along the lines that you see there. So let's take an easy one, like 100% H2O. That's the blue line, which is right on top, 100% water. If you build a planet, hypothetically, obviously, you can't really imagine that in this universe you'll have pure water of such huge proportions. We don't, and we don't see anything like that. But if you imagine that, then a planet like that will be less compressed than the Earth at one Earth mass. So it will be almost 50% larger in size, because water is lighter, less dense, and although it's compressible, it's not possible to compress it to the density of rock. And so that blue thick line with the dashed line in the middle shows you the best fit we have as of this spring again. Courtney Dressing is one of our students that just graduated yesterday at Harvard, and she did that study. And you see, uncannily, that line with its scatter, the blue shaded region, goes through Venus, Earth, and 5 of the exoplanets. Actually, all of the exoplanets which are known with good precision fall on that line. So more or less, to within limits, this is Earth-like composition. Rocky, with iron and other metals in a core, perhaps, with very little or no water. And then, as you go to 10 times the mass of the Earth, all hell breaks loose. You have planets with everything, a lot of water, a lot of rock, maybe hydrogen and helium. GJ 1214b there sticks out and probably has a thick layer similar to Neptune and Uranus of hydrogen and helium. But what really is of interest to us are those closer to Earth, because that's where we have the concentrations we're looking for. And there, the family of planets really breaks into 2 major groups: rocky planets, no water, and water planets, lots of water. And you see, typically, those would layer for both obvious reasons. Heavier elements sink to the center in the formation process of the planet. And generally, the lighter stuff is near the surface. So we expect that there will be a lot of water planets out there. And water, in those large quantities, is not necessarily a good thing, my colleagues, the chemists, tell me, because it's also a very dilute environment. So much water means that your metals, some of the phosphorus and stuff that you need for life as we know it, will be too dilute. Maybe mixed with the water, but not in the concentrations that you need. You'll have to freeze them. You have to do all kind of funny things. So one of the challenges there is to really compare water planets to true Earth analogs. And by true Earth analogs, I mean dry planets. All of you have been schooled, and that includes me, by talking and thinking about our planet Earth as the water planet, because it's covered with beautiful blue oceans. But those beautiful blue oceans are so shallow compared to the size of the planet that they're like the water vapor on the surface of your bathroom window in the morning. That's how thin they are compared to the size of our planet. And if you collect all the water that we know of, not only in the surface oceans of the planet, but also inside it, because there is some water inside, that's what it ends up, a little dewdrop there, the size of Texas. Everything significant is the size of Texas, I guess. Maybe not. maybe a little bit bigger in this case. But you see my point. The Earth is not a water planet. And if we are really looking for planets which have some water, but not too much, we have to be able to distinguish between them. And here, not much work has been done. Guess why? Because there is no such kind of planet, a water planet, in our own solar system. There's some water moons, but they're so tiny that this work on the moons, like Europa, is an example of a tiny, tiny version of a water planet I'm showing you here. Studying Europa is a very different thing. So what do? First, you try to think of what are the possibilities that matter to what happens on the surface. Because life, as we know it again, is a surface planetary phenomenon. It doesn't occur in the center of the iron core of the planet. Well, there will be three generic possibilities. It's either the water planet, where the water dominates and half of the planet is water, or even 20% of the planet is water. It doesn't matter. It's just water all the way through, meaning that if you have the conditions for liquid water on the surface, which is the habitable zone, we still want to be there, you have an ocean which is about 100 kilometers deep. And about 100 kilometers deep, some funny things starts to happen. The water is now so dense under its own pressure that it solidifies. Even if the temperature is high, it solidifies into ice, but no longer the snowflake hexagonal ice that we are so used to like or dislike, depending on whether you live in Boston or this winter. But an ice like ice 7, which is a cubical crystalline structure, denser than the liquid form of water, sits on the bottom and doesn't care much about whether the temperature is high. It's all a pressure phenomenon. That's very different geochemically, it turns out, from the state in which that ocean covers the entire surface, but still is less than 100 kilometers deep, and what is on the bottom is rocks. So then you have direct contact between the rocks and the liquid water. And suddenly it turns out is even different from the case which we have here on Earth, and curiously we've always had on Earth from the geological record, which is the case where some of the rock is always sticking above the surface of the oceans. So when you look at this picture, two questions beg to be asked. The first one is there any fighting chance for the Earth case to happen at all? I mean, it's such a very fine-tuning case. You know, you just have to have the right amount of water to cover thinly half of it, but not the other half. I mean, it takes very little more than the 0.02%, 2% of a percent, to cover the entire surface, and then you're in type number 2, the middle case, where the geochemistry changes. Or you're completely dry, no water at all, or nothing to speak of, Mars. So that is the first question. The second one, which we really need to know if we are searching for life remotely on the surfaces of distant planets, is what controls the atmosphere? Because that's what we are going to see. We're going to see the atmospheric features and the surface features. And you know, each one of those three scenarios, there is a different physics that controls what happens in the atmosphere. And we understand quite well now the Earth case. It's called the deep water cycle. Ignore the gory details here. This is an actual picture from a publication. But it is good enough to show you the basic idea here. Water that you see on the surface is only temporarily on the surface, but it cycles through not the center of the Earth, but through the mantle, the interior of the Earth, below the crust, comes back again, and what you see is a cycle which has negative feedbacks. If too much water gets drained out of the surface, these negative feedbacks push more back to the atmosphere and to the surface, and vice versa. Very interesting system, and it makes sense in a general way, not just for the Earth as a unique planet, but for this kind of planets which have a small amount of water. And it doesn't have to be anymore 2% of 1%. It could be even 1% of water, just most of it will sit in the mantle, and only a little bit will be on the surface, so that this cycling can continue and some of the rocks are exposed. Very interesting, but it works for one Earth mass, Earth composition. So we wanted to know, is this same idea going to apply to super-Earth? Because we see planets there bigger than the Earth, 20% bigger, 50% bigger. Interestingly, the same feedback mechanisms for the deep water cycle seems to apply to those bigger planets. Very interesting and hopeful that the Earth is not some freak accident, but there is a whole family where if you have a small amount of water, a few percent, you will have a picture like that that is more common, just either a complete water world, no continents, or a world in which all the water is locked in the mantle and there is nothing on the surface. So that's very important because it then answers the second question, which is what would control the geochemistry of the planet on the surface. In other words, the atmosphere. And here we again take a cue from something which we understand pretty well here on planet Earth, which is the carbon cycle, also known as the carbon dioxide cycle. Just briefly, the carbon dioxide as a gas is a very common gas in any rocky planet. It's not just unusual initial conditions here on Earth. So that very common gas would be in the big reservoir of the interior of the Earth, finding ways to come to the surface, usually through volcanoes and mid-ocean ridges, then accumulates in the atmosphere, sometimes a little bit too much for comfort. That's the same reason why carbon dioxide is not so good when you overdo it, because it's a greenhouse gas. But it's a self-regulating cycle because it then rains down, and where the red arrow shows you, the important chemical step there is that there is this interaction between the carbon dioxide dissolved in water that reacts with the minerals, silicate minerals of the surface, the rocks generally, and then completes the cycle as the plate tectonics renewal of the crust continues. So that works if you have exposed rocks. But what if you don't? If you don't have exposed rocks, as in a water planet, you're missing that important step. So the whole cycle has to be different. And that was a question which, again, was not addressed because we didn't have water planets in our solar system, so why bother study them? Study something which doesn't seem to exist. So the first part was there will be a layering of ices. I told you already about those high-pressure ices before you reach the silicates where the carbon dioxide will come from. The first order question is any carbon dioxide going to make it to the surface through the ice? The answer is yes. That ice, as solid as it is, like many other things, convects slowly. Takes about, as you see here, maybe 1 million years. But hey, 1 million years in the age of a planet geological record is nothing. So yes, the first thing is reaches the surface. It would reach the surface, but in a very different way than what happens here on Earth. Because under those high pressures, water, being the polar molecule and polar liquid it is in solid forms, actually would encase the carbon dioxide or methane or molecules that are volatile and want to come to the surface in particular crystalline structures. I pushed the wrong button here. There you go. We call them clathrates. And by the way, the low pressure forms of those clathrates have big interest to the oil extraction industry. If you remember the problem we had in the Gulf of Mexico, a lot of the problem that was dealing with what was happening near the bottom there with those forms of ice which are rich in methane, natural gas. But if you go to those planets which have higher pressure than anything that we've ever experienced or experienced here on planet Earth, you end up with forms of quadrates which were never studied before, like field ice, where the water arranges around the molecules in different ways. And you start having interactions between methane and carbon dioxide, which turn out that a very similar feedback mechanisms as to the deep water cycle, which works for the Earth crust, where quadrates are not important in that sense. And so the final point of this, it turns out, is that, yes, we are starting to understand what would control the atmosphere in a water planet, and that will be the clathrates, the forms of water that control which gases reach the surface and which are essentially encapsulated into the interior. And so now it seems that we will be able to tell the difference between a water planet and a rocky planet like the Earth, even though we only have the radius, the mass, and one measurement of the abundances of gases in the atmosphere. So you're trying to control 3 parameters: water, iron in the core, and silicate. With 3 variables, you can solve for that degeneracy which currently exists. So then the question is, do we have enough of those planets to really hope to have a search like this? And the answer is yes. Thanks to Kepler, we found, and that happened really in the last 2 years, that our initial estimates of how common Earth-sized planets are in the habitable zones of nearby stars were very underestimated. They were very low, very conservative, as you would say. So the current estimate is about 100 times higher than what our original values were before the measurements were complete. And it's likely that that number may go even further up. So for the kind of planets that are interesting to the search for life in the universe, in our own galaxy, we now estimate that probably between 1 and 5 billion planets are available currently for this exploration. Now, this is a very large number, but just remember, astronomy is about large numbers, and 10 to the 9, even 5 times 10 to the 9, meaning billions of planets, is not necessarily a large number in a very, very large galaxy. So what really is the game changer that happened in the last year or so is, what does this number mean to our chances to find some of those planets right next door? And this is what made the big difference and what is making the big difference. And that's why I'm talking to you about this today. Because 3 years ago, I would have told you this, but I would have told you have to wait about 20 to 30 years before we can reach the nearest of those interesting planets and do the studies we want to study, because our technology is not there yet. What this new measurement did 2 years ago is to change that timetable from 20 to 30 years to 5 to 10 years. So now we have the technology, even with telescopes like the Hubble and some of the ground-based telescopes, to study the nearest of those planets, because they're much closer to us than we thought 3 years ago. And that changed the game, both by shortening the timescales, but also giving us the confidence that we can do it, and we have the tools to accomplish this. And immediately, as this was coming through the data with the Kepler mission, which I was honored to be on the team, a smaller group from the East Coast already proposed to NASA to take advantage of this. That is, to go and find those nearest planets, which, thanks to Kepler, we know should be there. We just haven't found them. The Kepler planets, because it was essentially a statistical mission, were selected to be farther away so we could have good controls and do the statistics right. Now we know the statistics. We no longer want to improve the error bars on how common Earth-sized planets are in the galaxy. Now we want to find the ones which we can study. And this is what this space mission, already approved by NASA and going to space in 2 years, summer of 2017, is supposed to do. And we're pretty confident that it will be successful as long as everything goes well with the launch and goes to the right orbit. Because the statistical result from Kepler is very strong and very reliable. This then brings us to the actual question. So what are we going to do? We'll find the planets. We're certain of that. In about 2.5 years to 3 years from now, we'll have a list. So how do we do it? How do we find life on a planet that we cannot go to and take samples? In other words, how do we tell that all this green stuff is there that you see on that image? Well, the way we've used to do that already is look for the byproducts, and particularly the ones that are abundant and unusual and would stay in the atmosphere for a certain amount of time, so we can detect them. So this question, seemingly very difficult, remote sensing, has an easy part and a difficult part. The easy part is, do we know how to technically do this? It turns out, ironically, we do, because we've done remote sensing now for 60 years. Since Sputnik and the first satellites, we've been looking down on the Earth and know how to detect very small amounts of trace gases, and particular ones which are organic, like you see in this particular case from the World Soccer Cup in Germany, 8 years ago. The little telescope, that gray can that you see on the left-hand side, is actually a telescope with an instrument which we call a spectrograph, which breaks the light into its different wavelengths, creates a little spectrum, and looks for the fingerprints of a particular molecule, which causes some human beings to be very rowdy and cause trouble, alcohol. And on the right-hand side, you see one of those remote sensing images, and that glowing pixel there is somebody who had too many beers. You can see that, very small amount in the exhale of that person from very far, safely away from them. So that's what we plan to do with the exoplanets. And particularly, the geometry, which is afforded by transiting planets, the way Kepler and TESS are discovering, actually, the planets, also affords you to do this remote sensing very well. You do it by through light, passing through the atmosphere during the transit, the little eclipse, and you do it in emitted light just before the eclipse. You would say, well, we understand why the through light technique requires a transit. What do you care about seeing the day side in an eclipse? Can't you just see it for any planet that eventually will go on its orbit? Well, it's a technical issue, but it has to do with what engineers would call an on-off switch. Now you have it, now you don't, and you compare, and are able to extract a very weak signal out of the dominant signal, and you guess the dominant signal is the star here, not the planet. This is an exaggerated cartoon image of a tiny planet with a tiny atmosphere emitting or passing through. So we know how to do this technically now too. We've tried it on the bigger planets, exoplanets that we've discovered. For example, water vapor is very easily seen in this particular spectrum, as we would call it, a diagram showing you wavelength, color of light in the near infrared, that is in the infrared region, which is not visible to our eyes, but to our instruments, night vision goggles, one example. And in that particular band, you have a fingerprint, a spectral fingerprint of the water molecules in the atmosphere of that planet called HATP1b. It's a hot Jupiter. It's not an Earth-like planet. But these are our baby steps. We're learning how to use the technology. So the blue line, wiggly line, is the theoretical calculation of what we expect to see there. And the black squares with the error bars is what Hubble allowed us to see in transit for this particular one. So we know how to do it. And Hubble may be a little bit too small, even for the nearest Earth-sized planets. But the successor to Hubble, the James Webb Space Telescope, is just the right size for doing this. And that's coming online very soon as well, 3 years from now, hopefully. So we know how to do it. As I told you, the last part is the difficult part. What are we looking for? What if life on other planets is not the same as life on Earth? And in other words, do we know what are the signatures? Or are we only going to spend all our expensively built instruments looking for carbon copies of the Earth? Excuse the pun here, but really, this is the Earth as we know it today, and not even in its history. The early Earth had a lot of life, microbes on the surface, before they managed to transform its atmosphere to enrich it in oxygen. So the way we hope to accomplish this is in the lab. And this brings me to the last part, which is life in the lab. Because you need a chemical system which gives you feedback at how does the chemistry change when you change the environment. And any of the existing life forms that we have today on this planet are too sophisticated to give us that information in the lab or otherwise. So what we are trying to do now in preparation for these glorious new instruments and capabilities that astronomers are building to get the data from other planets, we are trying to do our homework in the lab and build what is a chemical system that many would call a minimal cell, artificial minimal cell, which is a chemical system which essentially allows you to simulate what life does with the actual chemical bonds and molecules that are necessary, but without the sophistication of any of the existing organisms on this planet. So you can see the feedbacks, and you can see what are the alternatives. How do you extrapolate from the example of the Earth to other planets? And then you know already that there are three basic components when it comes to the chemistry. The informational, which is represented in bulk by RNA and DNA, but in units, building blocks, the nucleotides. The compartment building aspect, which is represented by membranes, which the building blocks are lipids. And the metabolic, which you mentioned in your definition early on, which of course the proteins which are built of amino acids. And the problem for 50 years now, since we've known this, is that each one of those components seem to require mutually incompatible chemistries. So yes, we can do them, we can make them in a lab or in several different labs and bring them together, but under natural conditions, they wouldn't work. And that was realized early on when Miller-Urey, in their famous experiment, managed to produce with what appeared significant ease, amino acids out of the basic small molecules and components that you expected, and energy was provided by sparks. But that was also the problem. Because of the incompatibility between producing amino acids and other of the required building blocks, that very complex system, which, as it happens also in the 50s, we understood that part of the modern system in any cell, which involves DNA, that system was just too complex. People literally gave up on origins of life during that early time because suddenly they realized it's a beautiful system, but it's also very complex and incompatible as an emergent system, chemically speaking. People suggested a simpler version of that, called sometimes the RNA world, because they realized that RNA as a molecule, a cousin of DNA, has the ability of autocatalysis and can actually bypass the production of amino acids and proteins. But there was no way to even produce those building blocks of RNA, the nucleotides or the ribonucleotides, in a way in which you would call this a natural pathway. That was only accomplished 6 years ago in the lab of John Sutherland in England, where that polymer, which you see here as the RNA, is simplified in its main chemical blocks: the nucleobase, the ribose sugar, and the phosphate, the backbone building part of the single strand of RNA, which is not very different from DNA. And what they realize is that the old way of doing it, by simply decomposing that complex units system into its building blocks, would not work, exactly because the chemistry was incompatible. You had nitrogen-based and oxygen-based chemistry, which didn't work that way, going back. You couldn't even combine the two basic units. There was no natural way in which this could be accomplished. So what they did instead, by exploring the entire landscape, they found out that you can bypass this by systems chemistry approach and go through an intermediate molecule which nobody had thought about, with always the mediation of phosphate, which should be in the solution, and end up with what you need. In that approach, which is now in this glorious big picture, I just want you to see how complex this network of reaction appears to be. But actually it's simple, because in the same pot of solvents and small molecules, like hydrogen cyanide and similar products, you end up with the building blocks. And you end up with most of the amino acids. You end up with, now we think, all the nucleotides, and also the lipid precursors, the ones which are needed for the membranes. And so in a kind of a emerging pathway that we now see, driven not by sparks, lightning, like in the Miller-Urey experiment, but by UV light, you can hope to see in that big landscape of chemistry, of all the possible reactions, of all the possible molecules, those peaks, and maybe one, the one which we call biochemistry or life on Earth, being connected to the initial conditions, which are the surface of that multi-parameter space, by a pathway which somehow miraculously, but according to the rules of chemistry, in fact produces everything which took place maybe on early Earth. And maybe it was the RNA, which was the simpler system, maybe not. But the fact that this is a possible pathway is very essential in building the artificial minimal cell. Because if we build one based on that simple model, and that's pretty close now in being built, then we have a fighting chance of understanding the feedbacks which the planetary environment provides in the different planets, which we will be able to see. And one day, in 5 years from now, when the James Webb Telescope is out there, and we have those spectra of course, water and vapor in the atmosphere and carbon dioxide, and we see molecules that we didn't quite expect to see, we'll have a model system, chemical system, for a biochemistry in our lab to be able to say, aha, this is a possibility, that's a possibility, or no, this is pure geochemistry, it doesn't require biochemistry. So this is really the story I wanted to tell you, and to tell you how we live in a really historic time in which for the first time we have a chance to try and look for truly alien forms of life beyond Earth, and maybe we'll be successful and we'll understand our place, or maybe we'll come back empty-handed, at least for the time being, and we'll find out that, yeah, it's a pretty unique phenomenon, and we are quite special. Either way, it will be a great exploration, a great journey, and thank you very much for your attention.